Hello, welcome all to this webinar. We'll start in about 2 to 3 minutes from now. We'll wait for a few more people to join in. Thank you very much. Thank you for waiting, and hello to everyone, and welcome to this series of 5-axis simultaneous 5-axis webinars that we are going to have in the next coming weeks. One of the reasons why this webinar was important was to reaffirm the power of SolidCAM 5-axis, and also to show everyone what are the new things that are there in SolidCAM 5-axis. Okay, so without wasting much of a time, I would like to show you what is new in 2020, and by doing that, I also would like to touch upon some new items in our HSR HSM list, since it comes with me. So we are also going to see a bit of HSR HSM and majority of 5-axis, and the 5-axis will continue into the next few weeks when we continue with our webinars. Okay, so what was that we introduced in 2020 in SolidCAM? The major feature in 2020 was the new 3-axis roughing engine that we introduced. Why it's called new? Because it's completely written out from scratch, and it has got some amazing features. First of all, when we compare it with our HSR, we know that our HSR was not true 64-bit compliant system, although it was just ported on a 64-bit. The new Turbo Rough is a 64-bit engine, which means it utilizes all the cores that are available to it, the memory that is given to it. It utilizes everything to its maximum, and that's how the software works. The calculation speed here will definitely go up as your number of cores increase or your logical processes increase. So if you're working on a 4-core and you take the same part and try to calculate it on a 6-core, it'll be much faster. You go on an 8-core, it'll be even faster. 12-core, 16 core, so on, it'll be much, much faster as you start increasing your cores and the logical processors, of course. We also do what we call as a toolpath caching. That means, let's say I have generated this roughing toolpath, and the depth of cut is 1 millimeter. Now, for some reason, I want to go back and change this depth of cut to 1.5 millimeter or 0.75 millimeter. I don't need to reslice it again because the slice information is all available to me with me. That entire slice information is completely available with me, and I've cached that that information on a particular area of my computer. I simply go there, and it's like parametric thing. I change it. Once I do that, my recalculation is lightning fast. It happens much, much faster. It doesn't have to recreate everything again. Only the affected areas it knows, and it recreates the affected areas. Second highlight of Turbo Rough is the fact that you have now an option to define multiple surface offsets, which means you could define the entire model as one part, and then you could derive areas from there which need a different offset. For example, you see on your screen here, you've got one part which is having, let's say, 1 millimeter offset, and all the pink colored surfaces, I can select them as a secondary group of surfaces. Those are going to get 0.2 millimeter offset. I can put like this infinite number of groups with different offsets. So this is very, very essential for the mold and die makers, where they would like to give, let's say on the parting surface, they would like to keep very less stock, and for the area that needs the part area, they would like to have a bigger stock. So another very highlighted, this is one of the highlights of Turbo HSR. Strategies, well, we have got the hatch, contour, and rest roughing. All the three strategies are currently available with us in Turbo Rough. Rest roughing. The rest roughing in Turbo HSR is based on two technologies. It's either on the updated stock or previous tool, and it also could be a combination of previous stock and a previous tool. So it will find out the best possible areas to tackle and generate the toolpath only in that area. The retracts can be kept absolutely to minimum. In fact, in some of the parts we have kept the retracts to 0, so that the tool doesn't lift at all once it engages into the material till it finds another region. Then it will retract and go to the second region. Arc fitting in rapid moves to smoothen out those sharp corners, that's possible. You can specify minimum stock thickness above which the toolpath will be generated, below which the stock will be ignored, toolpath will not be generated. So by providing a minimum stock width, you can actually cut down those unnecessary passes that are there that happen on the scallop. You can do a local stock definition, which means you need not be dependent on the previous stock. For example, let's go back to this part here. Now, assume that the entire part was machined, and for some reason, some area needed reworking, so somebody fixed a small block of material in that region, and now you could go back to your roughing and you could say, I would like to define the stock by surfaces. So I will pick only those area, and the part will be the complete part, but the stock will be only the restricted area. No need to define any kind of contours or anything. Just define those 6 bounding surfaces, and that becomes the stock for that operation. Also, a very important feature is the undercut stock. I'm going to show you in this part that we are going to run today in generic 5-axis. It has got undercuts, so I will show you the effect, and you will appreciate that it dramatically cuts down the time when you compare it with our existing roughing engine that we have. Fixture collision. You can now provide fixtures as surfaces, or it could be a complete model, or it could be just curves. You need not have to have the entire fixture model sitting on your part. You can just say this sketch is my fixture. It will understand that that particular area need not be machined. It will leave that much area. You can also provide an offset to it, whether it's global, radial, axial offset you can provide to it. And based on the offset that you have provided, it will leave that much area and move to the other area. It will not machine the area of where the fixtures are. For example, you have clamps. So it will leave the area for the clamp and it will machine everything else. Also, pre-drilled holes. You can have pre-drilled holes as a definition, and every time the cutter comes, it will dip into that region where you have done the pre-drill and just machine the part, mostly for cavities. Another very important thing is the adaptive feed rate. You can provide the minimum feed rate possible on that particular job with the particular cutter, and SolidCAM will find out the engagement of the tool with reference to the part and adjust the feed rates dynamically on the fly in the toolpath. It might either, in most of the cases, it will only drop it down because 100% is my actual feed rate. So let's say it's going in a corner. There, it will automatically drop the feed rate based on the engagement it is getting with the part geometry. So this is a very useful feature for inserted kind of cutters. It increases your tool life, also provides a constant cutting condition. Dynamic holder collision, also a feature of Turbo HSR. It provides collision-free toolpaths. You can provide your holder, and the holder will be checked against two items, depending on what the user has selected. It could be checked only with the machining surface to see if there's a collision with the machining surface, or it could be checked with an in-process stock, the dynamic stock that is available at that given point. It will be checked against that. In most of the cases, the dynamic stock is the one that is to be used, but if you want, you could still use it against the machining surface. Of course, there's a possibility that you could provide both of them. You could say check against the machining surface and also check against the in-process stock. Remember, more number of options that you push it into calculation, the calculation time is going to come down or go up proportionately. Automatic ramping. You can just say, I would like to do automatic ramping, and then provide a fallback sequence or a priority sequence of ramping. So we have helical, zigzag, line, and profile. You can change the priority. You can say, I would like to first try a zigzag ramping. If zigzag fails, go to helical. If helical fails, go to line. If line fails, go to profile. So it will check each slice and apply a proper ramping that is possible with the geometry that is available, the space that is available to it, and it will apply the ramping accordingly. So you can see that in some places it is using helical ramp, in some places it is just using a line ramping method. So you can provide the sequence, you can provide the priority. Okay. This is with the Turbo HSM. The announcements mostly were with the toolpath quality. We have got a much accurate sharp motion now in Turbo HSM toolpath, and we provide a very small radius so that we don't damage the wall. A new operation, 3-axis undercut milling. It's a simple constant Z machining where you can just provide a model to it, and the cutters accepted are slot end mills or the lollipop end mills. Either of them can be given as a cutting tool, and the software will go, SolidCAM will go in all those areas where the tool can reach. It doesn't matter if it's straight or it's an undercut. If it's an undercut, it will try to get inside. But the most important thing here is it will take into account the shank geometry, and it will make sure that there are no collisions with the surface when it's getting into the undercut region. So it's a very safe area to work with, a safe strategy to work with. For example, the most common item that generally requires undercut milling are shoe molds. So if you have got a shoe mold and you would like to do undercut machining using a lollipop tool, you can just say, this is my model, this is the tool, this is the depth of cut, and it will ensure collision-free tool paths against both the part surface as well as the shank with the part surface. Let's come now to HSS and the Sim5X. It's more to do with Sim5X. First of all, you can see that we have now the progress bar. We no longer have some vague messages appearing. You know exactly where the operation is, how much is done, how much is remaining, so nothing is blind. The entire calculation progress bar is now available for all Sim5X and HSS operations. You can activate and deactivate options without getting into the let's say, for example, you want to do depth cuts and you just want to switch it on, so you can just select that and that will be done. This would probably, this you will not see it in SP0, but it will come in the subsequent sub-release of SP0. Multiple boundaries definition in a single HSS toolpath is now possible. Earlier, even if you defined it as a multiple, it would only take the first one and leave out the other two. Now you can define multiple boundaries in both Sim5X as well as HSS toolpaths. Extension of toolpath. Earlier, if you had multiple faces to be machined and you said, I would like to extend the toolpath, only the first pass and the last pass, the extension would be visible. But now, because of regions, you can now see that the extension is available for each region. Both the entry and the exit extensions are available for every region when you are doing the toolpath calculation. Screw machining. This was a major announcement that was done in 2020, and basically to do with the calculation times. Depending on the geometry, we are at least 10 times faster when you compare it with 2019 in calculation. In some cases, it is 20 to 30 times faster in calculation. So you no longer have to wait for the results. It's almost instant. You get the results quickly. Lead in and lead out definition is also available for finishing operations. Sim5X and HSS now comes with a new option called automatic clearance plane. You need not define the type, you need not define the height. You can just say decide or define automatic clearance plane, and the tool will get retracted in the proper direction using the automatic clearance plane. The height as well as the type will be decided automatically by SolidCAM. Right. So these were some of the enhancements that we did with respect to HSR, HSM, and Sim5X. Let's get to our part today. Okay, we have got a pretty nice part today to work with. And we are now going to be working with this part using all the functionalities that are available to us. So I have got a nice part here and also the stock. So let's open the stock. And that's how my stock looks like. I've already done the, you can see either I've milled it or I've done the wire cut and it's put on the holding fixture. The holding fixture is then held on a vise and the vise is then put on a 5-axis machine. So we would like to do the machining of this part. The machining of this part will see several operations. It will see some 2.5D operation. It will also see the new turbo HSR operation, and it will also see some nice generic functions. I would like to show you several of them as far as possible on this part, because in the next couple of weeks, we also are going to have different parts to work with. Sorry. Right. So let's start our operations. Now, what I've done is to simplify this entire exercise of showing you the toolpath. I have saved a lot of templates. And this has to be one of our USPs. When we do a demo in front of a customer, is we should have tons of templates, give a proper name, put them with the new version. They are automatically segregated and arranged, so we don't have to worry about it. Each template goes into that particular operation subtype. Use as many templates as possible. Show to the customer how easy it is to work with SolidCAM, and it's really pretty easy. So let me open the template today, and the first thing I'm going to do today is to do some facing operations on all the 5 sides. So I'm going to call my first template. So I'm using a 32R 1.2 high feed bullnose for my facing. So I'm going to drag it and put it on this here. I'm using a stock-based approach for my facing. Okay, so let me edit this. We also have a possibility to edit the template once it is applied. Let's put that value. That's my toolpath. That's the first toolpath that I've generated. The next one, I'd like to put on the side. Okay, let me edit this also. Okay, that's 0.3 millimeters. Calculate. Okay, let's take another template and apply it to the other side. I'm doing this because I would like to have a very precise stock for my new roughing operation. Okay, so that's the reason why I would like to do the facing, because my stock itself is about 10 millimeters plus on both sides. Okay. Sorry, it's already calculated. Let's drag on this out here. Edit. Unfortunately, I did not save it. I've saved it as a single pass operation, but I would like to do a multi-pass. So it's also very important that we show that once you apply the template, you could easily edit this toolpath. You can change the values whatever you want, and finally get the results what you're looking for. Okay, this is done. So we have got our toolpath perfectly done. Why I use the stock method is pretty simple. You can see that this particular stock is a shaped stock, and if I had not used the stock method, I would have got unnecessary passes here which would run in air. So in order to avoid those air passes, I'm now using the stock-based approach for doing my facing. Okay, so let's run the simulation a bit. Let's go into the Solid Verify. Okay, we have got the fixture, the stock, and everything ready. And let's quickly run. That's pretty fast. That's good. So we have now shaped the stock exactly to the size that I want. And now we could go ahead and apply our first operation of 3-axis roughing. And like I said, let me just switch off the stock now. I don't need it anymore. Okay, like I said, we are going to use the turbo roughing. All those features that I showed you, we are going to now apply those features. So I'll go to my template. I already have my template here in the offset, 3x rough offset. You can see that with 2020 now, each of the templates are arranged according to their type. So facing goes into all facing templates will go into the facing templates zone. Drilling templates will go into the drilling templates zone. Roughing templates with 3-axis will go into the 3x rough offset zone. So I'm going to just drag and put my template here, just apply OK. So this is our new roughing operation. So you have got contour, catch, and rest rough. So let's go to the geometry page. I'm going to spend some time, but remember that we are going to have a special webinar only for the turbo technologies a few weeks down the line. So, but still, I would like to touch on this because since I've used it in this part. So first of all, we are going to select our target. So this is our main target. And then I have got my subtype. So I would like to keep 1 millimeter offset on my entire target. Now, you could say, I would like to keep, let's say, on this face, I would like to keep 0.5. So go here, select, and you're going to select the face, maybe both of them. And here you can see that immediately you get an option to put a second offset. So I would like to put 0.5 millimeter for this. And you can do it for infinite number of groups. You can have infinite number of offsets, but trust me, it's not a great idea. Generally, there are 2 to 3 groups, not more than that. But the fact is that you can now define different offset for different group of surfaces. Now, what we do basically is from the target, we are going to subtract these faces, and we are going to have a different offset for that. And for the remaining target, we will have a different offset. Okay, right, but we don't need it. So I'm going to delete. We would like to keep 1 millimeter all everywhere. Stock, I would like to respect the updated stock. Okay, I don't need to define a fixture here because we don't really need it. Let's go to the tool. I'm using a 16R3 full nose tool. And here I'm saying with the dynamic holder collision checking, check with the in-process stock with the clearance of 2 millimeters. Okay. Now, if you can go into the feed control and you have got the adaptive feed rate here. So I'm going to switch on the adaptive feed rate, and I'll say the minimum feed rate that you can go down is to 60%. I would like to have a rapid approach and a rapid retract, and everything in between will be G1 with this feed rate. Only the first and the last motions will be in G0, whereas the motions, all motions internally will happen in G1. You can also provide, like HSS, feed control zones, but you actually don't need it because you already have an adaptive feed rate. You can have different feed rates for links, link between slices and link between regions. Okay, you need not use 15,000, maybe you can use 10,000 or 20,000, whatever you would like. Let's go to levels. You can see that in our levels, we have the clearance plane, and we have said that detect the plane height automatically. You don't have to put the value. The plane height will be decided by SolidCAM automatically. You only have to provide the retract distance, your safety, and your exit distance. And up to what level should the tool come in rapid or in G1 15,000 feet rate? Here I've said that up to my previous Z height. So if whatever may be my depth of cut, if my depth of cut is 1 millimeter and I've already done 5 millimeters, it will come to G1 15,000 to Z-4, and from Z-4 onwards, it will use the plunge feed rate. Okay, so I'm going to use also an arc fit for my retracts and other things with a radius of 5. Boundary, you can see that it's not essential in turbo roughing to use a boundary. Okay, because the moment you use the boundary, you're restricting the tool and telling the tool that you now cannot enter from outside. By providing just the stock and saying, I still have a center cutting tool, you actually tell to the software that you can approach from outside, but in cases you cannot approach from outside, you can ramp into the part. Okay, so it's not essential always to define boundaries with turbo HSR. You can skip the boundary definition if you have the stock definition properly. Passes, my depth of cut is 3 millimeters, and the step over can be given as a percentage of tool, or you could directly provide the step over straight away. Tolerance 0.1, and the limits can be automatically picked up by the software either based on the target or by the stock. So we need not define it, it'll automatically do that. Sorting, we are going to use a zigzag method. We can, if it's a closed cut, there are two possibilities, either possibility 1, possibility 2, so we can use direction 1 or direction 2, and we are going to machine by regions. Okay. You could also have, we also have a possibility to do adaptive step down. Now, what is adaptive step down? You can provide a range and a depth. Okay, so let's go to paint. So let's say I have a pocket, and I can say that, let's say this pocket is 75 millimeters deep. So I can tell to SolidCAM 0 to -50. My depth of cut will be 5 millimeters. -50 to -60. My depth of cut will come down to 3 millimeters. -60 to -75. My depth of cut will be 1 millimeter. So you can now provide a range, and you can have a variable depth of cut in a single program. It's sometimes essential, especially when you're doing deep jobs, that once your tool starts getting in deeper, you would like to reduce the depth of cut. You need not go with the same depth of cut. So you can have now a range. You can provide a range and a depth of cut, and it will apply it similarly to your part. You can machine the flatlands straight away in the very first attempt. You need not come back and then do another thing, another roughing operation. Smoothing, you can smoothen the corners, the final contour, you can smoothen the links, and you can also minimize the links. So it will link regions in such a way that reverse linking is minimized. So it did not come back to the same region after doing something, come back again and do the region again. So those things are avoided. Nothing much in the tool control. In the link, like I said, we have ramping. You can pick auto, and then you can set your ramping priority sequence. Okay, line, helical, zigzag. You set the sequence, and the software will pick the sequence based on the area and the profile. It'll pick the kind of ramping automatically. We don't need to provide gouge check unless until you are having collisions, but it's going to be very, very, very rare that you'll have collisions with turbo HSR. Okay, we have got both translate and mirror in this. We still don't need anything, so let's save this operation. Save the operation, and let's hit the calculate button. For people who are very interested, you can look at the CPU utilization. It was 100%, okay, because now it's almost done the calculation. So there's no more CPU utilization, but I'll keep this window going. So I get a toolpath. If you were an HSR fan or an HSR person who's worked a lot, you would realize that your stock ends here, but your passes are still going down there because the region still is on this side. Okay, but these passes are going in air. What would be our solution if we did not have turbo HSR was to create a surface here and forcibly stop the tool by providing that surface also as being a part of the part geometry. All those things are not needed. So let's edit this toolpath. Let's go into our geometry, stock. I simply select the stock as undercuts button, save it, and calculate. Okay, again, for people, we are almost touching 100% CPU utilization. Okay, since it's a pretty short calculation, you cannot see the CPU touching 100%, but trust me, all cores will be utilized 100%. Right, you can see the result now. It understands that the stock did have undercuts, and it was only doing air machining otherwise. So now it has taken the shape of the stock and also stopped the toolpath accordingly. Okay, very, very important features, because you could be spending at least 15-20% more time just cutting air and doing nothing else. Now, if you go, your customers or probably your own colleagues will also say that this could be removed off with editing, but then editing for me per se is a dangerous operation. the best thing is to generate properly without having to, take your scissor and start cutting it, because you don't know what would have potentially be the hazard of editing. So very important and a nice feature where it takes the shape of the stock and exactly machines it to the way it, the stock looks like. If there's an undercut, it'll exactly stop there. Very important feature. Okay, so let's move ahead and let's start with our generic 5-axis. I've been asked several questions several times. How does our software fare with X? How does our software fare with Y? How does our software fare with Z? How do we differentiate? Well, every software will have its pluses and minuses. Okay. In India, we say 1920. That's how it is. That's how the softwares today are. The difference is hardly or barely noticeable. What is more important is what you present to the customer. You should present a couple of things. One is the ease at which you generate your toolpath. If you're going to define everything in front of the customer, or if you're going to do everything even in front of your own user, it might sound that the software is a bit difficult. But if you create your templates, if you have your templates ready on your side, you can just keep applying templates. Over a period of, let's say, 1 year or 2 years, you would have generated several jobs in 5-axis. You could take 10, 12 of them and different ones and keep their templates ready with you. So you get an idea, you use this template. Straight away, apply, select the geometry, and the calculation happens. So this method of showing your software or running your demo in front of your customer, that creates a completely different image of the product. It shows that the software is really easy. In fact, SolidCAM is very easy. I would say when you compare it with others in 5-axis, it's pretty easy. So what I have done today is I have created a lot of templates, and we're going to use these templates and show how nice and powerful our generic 5-axis engine is. So let's start, first of all, because I have this area to be machined. I still have material here, so I would like to shave this material off and finish this face. What I'm going to do here is I'm going to use our swarfing engine. Okay, so I've got my templates for swarfing. So I'll go to Swarf Machining, and I have got the side swarfing. I just take it, drop it out here. Okay, what I just need to do here is to define the swarf surfaces. So I'll pick the swarf surface. That's my surface. And because, remember that this particular swarf surface has got two possibilities. The tool can come from here. The tool also can come from here, because we have not said from which side it needs to come. So in order to make sure that the tool comes from the proper side, we just will define two curves. The upper curve, okay, not that much, that's fine, and the lower curve. Okay, we don't want it to go there. Okay, that's done. And you show to the customer, look, my tool is all defined. Everything is defined. I simply hit the save and calculate button, and I get the toolpath. That's it. It doesn't take much time. So let me change the color so that the toolpath is visible. I'd like to change the color to yellow so that it's visible. Save and exit. So that's the toolpath, very neatly done. And if I now run the simulation or show you the HostCAD simulation, this is how the tool is going to look like. One pass, second pass, third pass. That's it. My face is done. Trust me, I was at a customer a few weeks back, and the customer recently had bought SolidCAM, and the user of one of the most powerful 5-axis solutions, the software, what I mean. And I sat with him because he became a nice friend of me, and I asked him, I would like to see some things in the software because I've heard a lot about it. So I asked him, just show me simple swarfing operation. Just take a straight wall and just show me the swarf, how the swarf works. The customer had used that particular product for a couple of years. So I believe when you used a product for a couple of years, we expect that you know at least some things in the product. But trust me, even a simple swarfing operation, which is not automated, okay, you had to define a lot of things. It was a nightmare in that product. But you can look, I've picked up a template, just came, applied, selected my geometry, my toolpath is done. I did not break any sweat on this particular toolpath. So the whole idea here is to tell you that as long as you're on the highway, when I say highway, what I mean is those automated functions like what we have, impeller milling, port machining, screw machining, as long as you're on the highway, most of the products are pretty much similar. Okay, then it becomes the strength of the user who's showing it. What does he show in that automated functions? But the moment you get down from that highway and go on a dirt track, like you come back onto a generic engine where you need to define a lot of things, that is where the whole game becomes, or rather changes. There, softwares which were once considered very powerful start faltering because the user would have never gone so deep into the product. And he perhaps doesn't understand. He has only been taught, or even the people who are working with the product are working only with the automated functions. Whereas here, most of our working time is spent working with the generic part of the software. So we know our generic engine inside out, how it works, and a lot of improvements keep happening every 3 months. Every 3 months, there's something new coming up. Okay, so the gist is take the dirt track. Don't go onto the highway right in the beginning. Okay, take a nice part. Over the next few weeks, I'm going to show you some very nice parts, and you can have those parts to show a demo to your customers. I'm going to prepare like what I've prepared the part here, including the fixture and the vise, everything. Okay, and also the templates. I'll send you the templates. Right. So our first 5-axis is ready. We will now take care of this pocket. Now, the moment I look at this pocket, even I was flummoxed. When I look at this pocket, I thought, oh, this is a 2.5D pocket. So I tried to do some sketch, and it just didn't select this surface. So it means that this is exactly not a flat surface. You cannot use a 2D pocketing in this, and you cannot do it. It will still need either a proper 3-axis work, or you could just run a 5-axis procedure, which is much more easier to work with. Okay, in 3-axis, you still need to create the coordinate system, a lot of things. But what I've done again, templates. So I would like to machine first the base face. Sorry, the base face I would like to machine first, and then I would like to finish the wall. So the base face I have done with the generic 5-axis using parallel to curve. So I've got the pocket bottom finish. I just take it and pull it back here. In the geometry, I'll pick this. Okay, I'll confirm this data. Obviously, it will not because it still needs the curve. So I'll pick the edge curve. That's my edge curve. And what I've done is I have kept a margin of 1 millimeter from the wall. So I'm not going to touch the wall. I'm going to leave 1 millimeter away. I'm going to be away from the wall by 1 millimeter. So all I now need to do is hit save and calculate. Okay, this is T3. Okay, let's look what T3 looks like. And this is my toolpath that's done. You can see we have provided a very nice ramp. Again, this is a trick I think everybody knows. For people who don't know how to apply this trick of ramping in 5-axis, it's pretty simple. Go to the link, go into the lead-in, And in the lead-in, you provide a height. Okay, you say I would like to have a height of 5 millimeter and an arc sweep. Generally, an arc sweep is 90 degrees, but here I've said 1,500 degrees. So let's say 1,000 degrees. When you say 1,000 degrees, the circle is 360 degrees. So it's going to make 1, 2, and 3, almost 3¼ circle. And those 3¼ circles are going to be distributed over a height of 5 millimeters, which create the effect of ramping. Okay, there it is. Very nicely done. It approaches inside, it finishes the floor, and retract. Done. Again, you can see here in the levels, I've used the clearance type automatic. I did not specify where is my plane, how far it has to go, nothing. I just said automatic and it's done. Right. Once that is done, I would like to now finish the walls with my generic. Now here, I would like to use a swarfing technique. Okay, so I'll go to my swarfing templates, and I've got the wall finish template here. I just drag it and put it into my tree. Let's define my walls that I would like to finish. Pick this and this. Okay. Say okay. Let's say okay. Okay. I expected that, so I'm going to use and drop it here rather than. So let's go to the geometry, swarf, surface. But in this case, I'm using a different way of using Swarf in this case. I'm just not going to use the automatic functionality of Swarf, but also going to provide a flow surface so that my tool goes there and stops. I'm also going to use tilt lines because I want to control the tool axis. I don't want the tool to dance in areas because some of the surfaces are not great because they have a different ISO lines, they have different widths. But that's the reason I would like to define tilt lines, simple tilt lines, 8 of them. So just pick 2, so the third, okay, fourth, then after the fifth one, sixth one. You will ask me why did I not save this also, but you know, I created a new part. I'm only using the templates for my parameters, okay, and the strategy, right? I have got 8 tilt lines. That's okay, and let's calculate. That's done. So I have now got the side machined also. It is not 2.5D, by the way. It has got some kind of draft, and if you look at how the simulation looks like in HostCAD, this is how it will look like. Neat. Again, here you can see automatic clearance plane. No need to define anything. Okay, that's done. Let's look, because it's a symmetrical part, that's the reason I'm doing only one side. Let's look at this region here, and I would like to now tackle this region. Again, I have got templates. Here I've used the generic 5x template. So I'm going to go parallel to the wall, parallel to curve, rather, sidewall finish. Okay, let's drop it here. Say, okay, let's open up the operation itself. My drive surface, 1, 2, and 3 drive surfaces. And my edge curve is this one. Reverse it. Okay, sorry. So let's pick the small things. Okay, that's done. That's okay. And let's calculate. That's the best part of templates. You just pick the geometry and your calculation is done. Again, automatic clearance plane. No need to define anything. Okay, you can see that. And the most important thing I missed, automatic arc. It uses dual arcs, horizontal and a vertical, and applies it according to the situation and according to the geometry. Okay, so 3 passes and my wall is done. Simple. Right. Now let's come to the main area falls that we need to be careful about. Although some of our technologies today can handle holes and other things as part of the links, a better way is always to close them when you're doing 5-axis, especially when you're using the circle end mills or our barrel tools. Okay, because now I'm going to use barrel tools to machine the inside of this region, the walls. I'm going to use barrel tools. What are the advantage of barrel tools? The biggest advantage with the barrel tool is that it has got a big radius, let's say a radius of 95 or even 100. And to get a similar scallop, let's say I want a scallop of 2 microns. If I want to get a similar scallop with a ball nose end mill of, let's say, 10 diameter or 12 diameter, I need to define a step down of anywhere between 0.1 to 0.2 millimeter to get that scallop. With a barrel tool, I can get the same scallop by going up to 1.1 millimeter to 1.5 millimeter depth of cut. So your machining time dramatically comes down. But with barrel tool also comes a lot of challenges. How do you handle those challenges? Okay, so what I'm going to do now is I have got some surfaces that I created, which are basically the untrimmed surfaces. Sorry, so I'm just going to switch on those surfaces. Okay, those are the surfaces that I've untrimmed and kept ready. Like I said, with circle end mills, you need this. I'm going to show some other things where you don't need to do all these things. Okay, right. So let's apply another template. This is going to be a very nice exercise today, where we're going to do a lot of template-based machining. So I have an oval form tool with 5-axis, and I'm going to apply it here. Okay, it's morphed between 2 curves. So my drive surface, 1, 2, 3, 4, 5. These are my 5 drive surfaces. Saying OK. Since it's morphed between 2 curves, I would like to define my curve. Of course not. That's not how I want it. Let's pick curves manually. Okay, that's done. Say OK. That's my first curve. The second curve, I would like to pick here. Nope. I always keep forgetting that I need to switch off that tangent propagation, but that's fine. Doesn't take much time. Okay, that's my second curve. That's done. So the tool here I'm using today is from Emug. It's a oval form tool, diameter 6, with the bottom corner radius 1 millimeter and the profile radius 95 millimeters. So I'm using this tool today. And the area that we need to focus ourselves on is the tool axis control. We need not define any angle with oval form or with barrel tools. You can just specify on the barrel form. For example, let's go back to our paint. Let me save this. So I have got this form here, the oval form. Okay. So what you have here is the barrel section, On the barrel section, we have got a line parameter. Now, what it means? It means that I consider the bottom where my barrel section, this R95, is finishing. Okay, this is the R95. The bottom area from where my other radius starts, that point is considered 0. And the topmost point from where my shank starts is considered 100. So I can specify, this is 0%, 100%. So I can specify a point on this barrel profile or oval profile, let's say at 30%, and I can tell to SolidCAM that keep maintaining this point in contact with the surface every time. So the moment I specify this point, SolidCAM will automatically derive the tilt angle and maintain the tilt angle throughout when it's machining the surface. So it becomes much more easier. Now there are a couple of methods. One is you could keep it constant at 30%. The other one, you could say start at 80%. Your first engagement will be at 80%, and you finish at 15%. So it will keep varying the depth of cut over this profile. Very nice feature. Thereby, you increase your tool life because you distribute the wear evenly on the cutting edge of the tool. Okay, but here, what I've done is I'm using 30% as my contact. Perfect. Let's go to the gouge check, and I have got the tilt tool. Now, in tilt tool, we have got something very nice for barrel tools, and that is smoothing. Okay, so the tool path will be automatically smoothened when it detects collision and it tilts. The tool path will get automatically smoothened out. You won't actually see anything on the tool path. It looks so nice, clean, and smooth. And this feature is enabled only if you select any of the barrel tools: oval form, taper form, or barrel form. Okay. So with the drive surface, I'm going to tilt. I'm going to tilt against only the tool tip and the arbor. I'm not bothered about the tool shaft. And my second gouge check is against the surfaces at the bottom, where I'm going to just trim and relink those surfaces. So I'll pick those check surfaces for me. These are my check surfaces. Okay, and this one. Perfect. That's done. Let's save and calculate. Perfect. So we have a nice tool path. Let's switch off the surfaces that we opened up. And I have a pretty nice tool path here. Very nice entry. And you can see what happens even at the corners when it gets the collision and it does the auto tilting. You can see that even those areas have been smoothened out. Very nicely done tool path with a barrel tool. Okay, with an oval form tool, circle enders. This is what we have to call them. So this is how the simulation will look like. And you can always see that it will always maintain that 30% point on the tool. So my 30% point will roughly come somewhere here on the tool. So that's the 30% point that it is constantly maintaining throughout the cut. Even when it goes down, it will still keep that point in contact. So several of the passes at the bottom will stop. They will not be machined because I've told the software that you need to maintain that 30% always. Okay, good. Now let's go to another very nice, interesting function in SolidCAM 5-axis. I'm not sure many of you are using it, but after you see today how it is to be used, most of you will shift all of your generic 5-axis to that function. I'm talking about multi-axis constant step over. It's a underdog, you can say, but when you look what it can do, you'll perhaps stop working with everything else and start using it to the maximum. Multi-axis constant step over basically is a pattern generating function in our generic 5-axis. It's nothing special because everything else is the same as our generic 5-axis, but what is crucially different here is that the kind of step over it generates is constant. Irrespective of how you measure it, you'll always get constant step over. If you have said 0.5 millimeter, irrespective of from which side you're looking and which side you're measuring it, you'll always get 0.5 because the step over is distributed looking normal to the surface and not looking from a particular direction. Okay, so very important. Again, I have got my templates for that also. And what we are going to do is I'm actually going to machine the floor of this area. And here I'm going to use the multi-axis constant step over. So here I'm going to use the multi-axis constant step over. And I already have the template ready. So I'll just drop it here, say OK. And what I will do here is I'll just switch off some functionality that I'm going to show you later. Okay, so this is my multi-axis constant step over. I can go and pick my machining surfaces. It could be a model. You can provide the entire model as your machining surface and work only in a certain area by defining your drive curves and boundaries, or you could be specific like you work with your generic 5-axis. So I'm going to pick the surface. Okay, this is done. And it's going to be parallel to multiple curves. So I'll define the curves. Pick this. Okay. Okay, that much is done. Let's go here. Okay, to accept. That's done. Let's say okay. Now let's go to my gout check. I don't think we do have the check surface, and it's with, I'm going to use the tilt tool, and I'll define all of these surfaces as my check surfaces for tilting so that it doesn't collide against the surface. Okay, and in the toolpath parameters, I have defined my maximum step over as 1 millimeter, or I can say constant step over as 1 millimeter. Okay. Anyway, either of them, let's save it. Oops, the 2D boundary is empty, so it has to be contour 7. So I'll go into the constraint boundary and I'll say contour 7 also as my boundary. And let's hit the calculate button. This could take about approximately a minute. Okay, that's done. Now, one thing you'll observe very immediately, why is it not getting into those holes? Although I selected this surface, it didn't get into this area at all. It just went over that area. Okay, that's because if I go into the geometry function and go into the advanced, we have got a function called as fill holes. So if you have gaps in between, which are basically holes or cutouts, it will internally fill them with surface. And you could also say that don't give me any passes on the holes. So it will avoid those areas. Otherwise, sometimes if the cutout is pretty long, you're only going to waste a lot of time moving on that in that region. Okay, so I use the fill holes option, and this is my result. Now, what I would like to do here is, actually, I would like to show you the problem. Because the toolpath looks nice, but we have some other issue here. And I would like to take it into the machine simulation. And the moment I show you the problem, many of you will nod your head and say, yes, we have got this problem tons of times and we have no idea how to fix it. So my toolpath looks very nice here. But when I go into the analysis and go into my tool number, you'll see this. the retracts. This is basically because the machine construction is such that it needs to rotate the part at that particular point by 180 degrees to machine the other area. So we have a feature in SolidCAM that whenever the difference between 2 points is beyond a certain degree, the tool will automatically retract to the safe plane, allow the part to rotate, and then come down. Okay, but you would have seen this many times, and most of you don't have a clue where it is coming out from. And why I showed you this is because this is a very typical surface. No matter what you do on the surface, you'll always end up with these retracts. It's a very, very typical surface. It's also to do with the machine construction, the 5-axis machine construction. So what we are going to do is slightly different. I have another surface. I've just filled the holes. So I've got another surface here that I have, okay? And I'm going to edit this toolpath. And instead of that machining surface, I will define this as my machining surface. Okay, perfect. But just defining the surface doesn't solve the problem. There's another nice feature inside our generic engine, which again I'll call it as an underdog because I have not seen many people show this function or use this function. And that's in the tool axis control. If I go into advanced, we have a function called as a maintain common tool axis. What this basically is going to do, this basically will try to find the best possible approach to the surface in such a way that it can lock the two 5-axis at the 4th and 5th axis. It can lock at that particular angles and machine the entire surface in pure 3-axis. Although we have set 5-axis, but the result is actually going to be a 3+2 result. And this exact angles are going to be found out automatically by SolidCAM. Okay, it's amazing. It's an underdog again. Let's calculate. I think we have a small issue here. So I'm going to stop this calculation and I'll open the file in which we can see this result straight away. Okay, so we have the result straight away here. Sorry, not this one. You can see what happens here once you define that. If I go into the simulation and go into the machine simulation, yes, because this is of the automatic clearance plane, you can see what has happened to the axis values here. The A-axis is locked at 23.505 and the C-axis is locked at 93.862. Now this is determined by the software automatically. And now if I go to the analysis and look for those crazy retracts, you will see that you don't find any of them. Okay, one of the ways you can solve many of your problems is to use the common direction. It's It's a relatively underutilized functionality in SolidCAM. We can see that it's completely 3-axis now. Complete collision-free 3-axis machining. You don't need to define or make any 5-axis toolpaths. It's a very powerful 3+2 functionality available inside the simultaneous 5-axis engine. You also know that when you do machining by locking your rotary axis and swivel axis, the surface quality also improves dramatically, okay? Because you're not utilizing all the 5 axes, you're only utilizing 3 axes, the X, Y, Z axis, and locking the other 2 axes. Okay, sorry for that goof up. Let's go back to our file. Now I'll quickly show you another area where we can apply the multi-axis constant step over, and that is to machine these surfaces. Okay, again, these are having holes, but we will not do any kind of patch up or any kind of surface generation. So I'm going to use the sidewall finish template that I already have. Drop it here, say okay. Sorry. Let's go to the geometry and machining surface. 1, 2, 3. Done. And since it's going to be parallel to curve, I'm just going to use my drive curve, which is the bottom curve here. Okay, that's it. That's done. The tool, it's a 10 diameter ball nose, and I'm giving a 15-degree tilt to it so that I use the ball or the ball side of the tool, the radius of the tool, to machine it. Let's save and hit the calculate button. Done. You can see I did not close this area, neither I went into the link and said join direct. Okay, it's closing the holes internally inside SolidCAM and then performing the operations for machining. Very neatly done. Okay, we can do the same operation also for the middle pocket. This one, nice and clean operations. I urge everyone from today, you know this functionality of multi-axis constant step over, please use it. It's a very powerful functionality, but the only thing is that this functionality can be used only if you're using in generic parallel to curve or morph between 2 curves. Currently, the multi-axis constant step over is available only with parallel to curve and morph between 2 curves, but this should be good enough for you. It can create really very powerful and clean toolpaths. And most important, it works on mesh, doesn't directly work on surfaces. So it creates a very, very clean toolpath. Let's go to the geometry again. Machining surfaces, 1, 2, 3, 4, 5. These are the 5 machining surfaces. And the drive curve, of course, will be that. Okay, simply hit save and calculate. Check this. Sorry. Okay, since we are using a bigger tool, I would like to provide these surfaces as my check surfaces. Okay. Contour 9. So let's use contour 9. Let's calculate. Oops, sorry. It was an open curve, so it couldn't calculate. Perfect. Result is done. Ready. Clean toolpath again. You can see how nice and easy it is to work with the generic 5-axis once you have got your templates in place. You can just keep applying, dragging, and working with the part as if you're working with some simple 2.5D geometry. You can create tons of templates, and based on the geometry, based on your judgment, you can easily apply those templates and work with generic 5-axis without getting into the depth of the template on how it has been done, why it has been done. You know it works, you apply the template. All right, so we have completed day one. It's like 1 hour 15 minutes today. We have completed day one of our webinar. I assume that we will have at least another 4 of them, because I have got some very nice parts to show you for more generic technologies that we can apply on those parts. Almost all of them are either general engineering or aerospace parts, and we will also take in the next week one application-based strategy. I think it'll be screw machining, because since we have done a lot of improvement, I would like to show screw machining along with the generic part itself. So if there are questions, you can ask me questions. I believe there are some questions already. Missing the approach and retract link on every size. For which is this, Marcus? Maybe Marcus, you can get in touch with me over Skype and ask me what it was. I can send you this part. But I think in some of my templates, I have not used leads and links, just to show that you can always go back, edit, and do the toolpaths. If there are no more, there's another question on how to use tool compensation for swarf milling. At the moment, we do not have tool compensation for swarf milling. In event that you would like to use a swarfing kind of a technology, then I would suggest you to go back to our generic machining. So if I go into not this one, sorry, on the swarf. If I go into the generic technology where is it? Sorry, we moved several of things here. Here it is. We've got the 3D tool compensation. So we currently don't have it on Swarf, but we can definitely take it as a feature request and see how quickly we can get the tool compensation back onto Swarf. But in event you would like to use a tool compensation, just ensure that you use the generic 5-axis, and you can use the tool compensation for generic 5-axis, provided your post processor is supporting the tool compensation functions. All right, if there are no more questions, I will end this webinar here, and it was really nice having you, all of you, attending this webinar, and I hope to see you again next week, where we'll take another interesting aerospace part, and we will see how to machine it using our generic 5-axis. We will also move into another interesting area of screw machining, because I think there are quite a lot of different views on screw machining. I think the name itself is not right. It's giving the view that it can be only used for machining screws, but that's not the case. We will see how screw machining can be used to machine different parts. They're just not screws. They can be anything. Different parts, how they could be applied, how screw machining could be applied to machine those parts. So the webinar next week is likely going to be even more longer than today's webinar. It's going to comprise of an aerospace part as well as a part, few parts for screw machining. Thank you very much for attending, and have a nice day, have a nice evening, have a nice night wherever you are. Thank you once again.